All right, these are the 3.11 notes. I know we're in chapter 4, but this was a topic that was in chapter 3 that we decided fit better into chapter 4, part 2. So what we're looking at is a topic called related rates. And I'm hoping that when you see the word rates, you are thinking of a derivative, a rate of change. And these are going to be rates at an instant, which will fit really well in with derivative. The rates are called related rates because we'll have some type of equation or formula that will tell us how different variables relate together. Some type of equation or formula. And then we want to be able to find rates here. And usually these rates, instead of being with respect to x as our input variable, we'll be doing with respect most of the time to time. And we could find the rate of change of a variety of different variables depending on our equation, but most related rate problems are with respect to time. And something that's interesting is you might not even have time in your equation. Think back to when you did parametric equations in pre-calculus. It's that idea of this third variable, but the third variable may not even be written into the equation. Could even be a fourth variable. May not even show up in the equation. In fact, usually it doesn't. And so since we're trying to take a derivative of this variable that's not even in the equation, what we will use is we will use implicit differentiation. But maybe not in the way that you would expect. You're going to get really good at it, but maybe the first time or two it'll seem a little weird. So here's an example. Let's say a particle is moving along a curve. And its position can be modeled by this function, y equals blah. Notice that y and x are the variables. If the rate of change of the horizontal distance is 4 feet per second when x is 5, then find the rate of change of the vertical distance in feet per second. Okay, I really want to start with the if part here, and I'm just going to translate this. We're talking about a rate of change, that's a derivative, of the horizontal distance. Well, horizontal would be the x variable. This right here is talking about the rate of change of x, and it's with respect to time. You might wonder how I knew it was with respect to time. It was actually because of these units. That denominator here being seconds tells me that this is with respect to time. So the rate of change of x with respect to time is 4 feet per second, and that's happening specifically at the instance when x is 5. X could have a different rate of change at any different moment. So we need to know this specific moment that we are finding the rate of change, or we are given this rate of change of. And remember, this matches what we know about derivatives, because derivatives are rates of change or slope at an instant instead of over an interval. Continuing on with this problem, we want to find the rate of change of the vertical distance. So what we're trying to find is the rate of change, that means the derivative, of y with respect to x, or with respect to time again, because this is in feet per second. So they're kind of helping us understand that this is with respect to time with some of these labels for units. Well, when you were in Algebra 1, you learned that, if you've got some equation, you can pretty much do whatever you want to that equation as long as you do the same thing to both sides of the equation. And since we're trying to find a rate of change, we are going to start by taking a derivative. We want to take a derivative, and because this is an equation, we have to take the derivative of both sides because you have to keep the equation balanced. So just like in Algebra 1, you have to do the same thing to both sides. It's true with calculus as well. But we're going to take these derivatives here with respect to t. And this is going to be our first step. So I'm going to go through here, and I'm going to take the derivative of each one of these terms. Now, the derivative of y is 1, but I'm doing this implicitly with respect to t. So I have to multiply this times dy over dt equals the derivative of 3x squared would be 6x, but x is the wrong variable. I need to do this with respect to time. So back when we've done implicit differentiation so far, anytime you took a derivative of y, you had to multiply it by dy over dt. But since we're treating t as our input variable, anytime you do a derivative of any variable that's not t, you're going to have to do this process. Plus, the derivative of 6x is 6 times dx over dt. And then the derivative of any constant is 0, so I don't need to do anything there. I've now done the calculus. I'm now going to customize this relationship here for the instance that I'm looking at. And so they'd given me some information, so I'm now going to use substitution. It is important that you do not use substitution until after you've done your calculus. There is one exception to that. If you have a variable that is unchanging and it's just a constant for that problem, then you are allowed to substitute into the equation right away in that instance only. But that's less common and that's not your normal practice. Okay, so I'm going to go through this and I'm just going to substitute in wherever I have values. dy over dt is what I'm trying to find. So that will remain my variable. X in this problem is 4 and dx over dt is, x is 5 and dx over dt is 4. And then I'm actually replacing dx over dt again here. So dy over dt would be 120 plus 24 or 144. And they already did tell me the units, which would be feet per second. Most related rate problems will have units, not all, but most. And so if units are mentioned, you need to include units in your answer. Let's take a look at number 2. There are 2 parts to number 2. Again, we have an equation with x's and y's, but what we're finding is dy over dt. dy over dt, so notice we have the wrong input variable here, so I'm going to need to use implicit differentiation. And then I have some things I already know. I am going to follow these same steps. Whoops, didn't mean to do that. Let's see if I can undo that. There we go. I'm going to do these same steps that are right up here. I'm going to follow these same steps for all my related rate problems. So since I have the equation, I can go ahead and start by doing the derivative. So I'm going to use the power rule implicitly with respect to x for each variable, or with respect to t for each variable that's not t. And keep in mind that the derivative of a constant is 0. Sometimes people forget that and they keep that 25 there. By the way, if you wanted, you could at this time divide all of these terms by 2. It's not required. So what I'm doing right here is not required, but it is a nice option because if you are not allowed to use a calculator, then the smaller numbers might be easier for you to compute. All right, so I'm going to take, and now I'm going to, I did the derivative, so now I'm going to do the substitution piece and rewrite this equation that I just divided everything by 2 by this derivative equation. So we could call this a differential equation. We'll talk more about those later in the year. But x is 3, dx over dt we are told is 8. Y is 4, dy over dt is what I'm trying to find, so that's going to remain my variable. So I'm going to move the 24 over to the other side to get negative 24, and when I divide that out, dy over dt is negative 6. Now I'm going to check the problem to see if there's units. If units are given, they must be provided in the answer. However, no units are given, and so I'm going to go ahead and call that problem complete. I'm going to encourage you to stop the video and try part B on your own, and then restart it when you're ready. Part B is still using the same equation, which means that my first step, which is, again, to take the derivative with respect to time, that hasn't changed at all. And so I can actually just copy down what I did prior with the derivative. And if I wanted, I could divide again by the 2. So I really could have used that yellow one. This time, I guess I'll keep the 2 in for no other reason than just to show you that you are allowed to do that. So x is 4. Dy or dx over dt is what I'm trying to find this time. So it's my unknown. plus 2 times y. Oh, interesting. We were not given y. That doesn't mean we can't find y. It means we have a little bit of different work to do, so I'll come back to that. And then dy over t is negative 2. Well, we have an equation that they gave us at the beginning of the stem of this problem that tells us how x and y relate to each other. And so I could use this equation to find a missing variable. Not a missing derivative, but a missing variable. So since x is 4, I can use this to solve for y. The interesting thing here on this one is that we actually get 2 answers for y when we square root both sides. Y could be plus or minus 3. So there's 2 different answers here for y, which leads me to guess there's going to be 2 different answers here for dx over dt. So I'm going to rewrite this really quickly as, just simplify this, 8 dx over dt. And then I have 2 times plus or minus 3, which would be plus or minus 6, times a negative 2. Well, that's kind of interesting. I mean, numerically that's a 12, but what's happening with the signs? Originally this was plus or minus, but I multiplied it by a negative. This is now minus plus. It's a very minor topic, and I know that feels super weird the way I just wrote that, but that is correct notation. Now, alternatively, what you could do is do this equation twice, once with a positive 3 and once with a negative 3 if you're really unhappy with that. All right, I'm going to now move that minus plus 12 over to the other side, and it would have yet another sign change. And when you have that other sign change and you move it back, the negative becomes a positive, the positive becomes a negative, it goes back to plus or minus 12. And then if I divide by 8 and reduce my result, I'll get plus or minus 3/2. Again, there are no units in this problem, so I do not need units this time. Example 3.